The word of the hour is differentiability, and we're going to talk about it. Okay, it's not just a fun word to say. Differentiability, differentiability. I mean, it is a fun word to say, but it's not just a fun word to say. All right, I'll stop now. In this assignment here, we're talking about finding out where a function is differentiable, and then talking about what's happening where it's not differentiable. So, again, if a function is differentiable, all it means is if you see the word, I'm going to write it out here, differentiable, all that means is you can, well, hopefully you can, but it's possible to find f prime of like a. Okay, so differentiable, let's write differentiable at x equals a means arrow. You can find f prime of a, or even better than that even is f prime of a is defined. It's probably better mathematically speaking. Okay, all it means is the derivative is a number. It means it has a slope. Now, the first thing we're going to do, well, let's just look at these problems, I guess, rather than me just rambling here. Clear this. Okay, we're looking at f of x equals 1 over x. And we know that to be differentiable, it must be continuous. So that's one thing. We need continuity, because if it's not continuous at a point, then it can't be differentiable there. So automatically, f of x equals 1 over x is not continuous at 0, since f of 0 is undefined. So let me get that out of there. We need continuity, great. But we're going to say immediately that x equals 0 is a point of non-differentiability. And what's happening there is f of x is not continuous. So put a colon or something. Okay. So that is one point. Now, in order to find any other points, we're going to look at the derivative. Okay, so f prime of x is a very easy function to derive. F of x is easy to derive, so it's just negative 1 over x squared. You can do the long way if you don't know the shortcut rules, but the power rule tells us it's negative 1 over x squared. And now we're going to look and see, well, where is this new function? It's the derivative, but it's just a new function. Where is that not defined? And that is not defined at the same point, x equals 0. And that's always going to happen. If a function is not continuous somewhere, then the derivative will not be continuous at that point as well, because if a function is not continuous, you're not going to be able to find the derivative. So mathematically, it's just always going to happen. So that's why that happens. The reason we derived it is we're going to look and see if there are any other points where it's not where the derivative is not continuous, and there's not. The only place this thing's not continuous is at 0. And remember, when you talk about continuity for us, what that means is we're looking for dividing by 0. You can't do that. Square roots of negative numbers. You cannot do that. And logs of non-positive numbers, which would be 0 or negative numbers. Can't take those. But in this case, x equals 0 is the only point of non-differentiability, and it's because f of x is not continuous. So in order to write, like I've been rambling here and just writing this crap down kind of in the margin, but my real answer would look like this. I would write f of x is not differentiable. I'm going to write diffbul, but it really means differentiable. Don't write that on a test or anything. But f of x is not differentiable at x equals 0 because f of 0 is 1 over 0 is undefined. Meaning it's not continuous there. Okay? Now, the question said find all values where x is differentiable. Well, just like with continuity, it's easier to find out where it's not differentiable and then list out the regions. So this is what's happening at the point of non-differentiability. It's not defined there, so that's fine. And we can say that f is differentiable everywhere else. F is differable on, and since it's everywhere else, you can write negative infinity to 0, union with 0 to infinity. It's everything but 0. Or, if you don't like writing that, you could write all the reals except x cannot be 0. So either one of these, either this thing or this thing would tell where f is differentiable. Okay. I'm probably doing a lot more work than you really need to be honest. G of x equals square root of x. Well, the first thing we're going to say is that for this function to have any points at all, for it to be defined, I guess, g of x is only defined if x is greater than or equal to 0. So it's not going to be differentiable anywhere less than 0 because there's no function there. No problem. The second thing we're going to do now is check out g prime of x. So we're going to get 1 over 2 root x is the derivative. And this is not defined at 0. So you can write that g prime is not defined at 0. So this is a g, sorry, g of x not differentiable at x equals, I'll write 0 equals x, but x equals 0. Okay, now, if you really want to find out what's happening there, the reason it's not differentiable is kind of twofold. The first reason is because root x starts at 0, and in order for something to be differentiable, the slope from the left and the right have to be the same thing. So if you like at this point here is a function, and you want to say that it was differentiable there, you got to check the slope from the left, slope from the right, and say they're both the same number. Well, root x doesn't have a left side at 0. Root x looks like this guy. Let me draw it up here. Okay, at 0, it's just starting out. So there is no left side, so it can't be differentiable at 0. But it could be right-hand differentiable, which is the same idea as right-hand limit. You're going to take the derivative from the right-hand side. And that's what I'm going to do here, because I really want to explain what's happening at this point of non-differentiability. Okay, so answering the first part, where's it differentiable? You're going to write g of x is differentiable. And again, diffable was on right, on 0 to infinity. Okay, the only problem point was 0 and all the negative numbers, of course, but 0 is on the function because g of 0 is 0, but the derivative was undefined there. So we're going to write this. At x equals 0, we're going to check this out here. The limit as x goes to 0 from above, and we're only looking from above at the right-hand side because, again, g is not defined on the left-hand side of 0. That's why we're doing this. We've got this going on. G of x goes to 0 of g of x is just 0. That's an easy one. The limit as x goes to 0 from above of the derivative, however, is, remember, the derivative was this guy. 1 over 2 root x. As x goes to 0 from above, well, we're going to get 1 over 0. And if you remember, that means there's an asymptote there on the derivative, not on the original function, okay? Always keep them separate. G of x and g prime of x are different functions. G prime of x tells you the slope of g of x. Now, as x goes to 0, we're going to get 1 over 0, which means there's an asymptote, and the answer is either infinity or negative infinity. And since we're coming from the right-hand side, we know there's definitely going to be an answer. It's either going up or down. And as x goes to 0, the square root of x on the right-hand side is always a positive number. So this is, the bottom's getting smaller and smaller and smaller and smaller, but they're all positive numbers. And 1 divided by positive numbers that are getting smaller, there's my dogs, is going to go to infinity. It's going to head to infinity. So what's happening there is a point, it's 0, g of 0 is 0. However, the derivative there is infinity. So, let's clear this junk out. So you would write, alright dogs, I hear you, calm down. There is a vertical tangent. And it's a vertical tangent because the slope, the derivative, is headed towards infinity. And if you recall from Algebra 1, there's a vertical tangent at x equals 0. So g of x is not differentiable at 0. That's why it's not differentiable at 0. A vertical tangent is, if you think about lines, if this is a line here that's got a certain slope, and then another line that looks like that would have a steeper slope, a line that looks like that has an even steeper slope, even steeper, and then the slope's just getting bigger and bigger and bigger and bigger until you get to a perfectly vertical line. And we always said that slope was undefined, but another way of thinking about that is thinking it as an infinite slope. And that's what we just saw when we did the limit as x went to 0 from above of the derivative. We saw that the slope was going to infinity, which means there's a vertical tangent. And if you think about square root of x, it looks like that. If you drew a tangent line to it at 0, it would be this dotted line right there. It would be perfectly vertical. And that's why it's not differentiable there. You could talk about what's happening there, because there's a point. It's just the derivative is not defined because infinity is not a real number. Okay.